Someone dies in cardiovascular, not because medicines lack time, but it's because warning signs went unnoticed. A heart under silence says oxygen is going to be dropping, or a body overheating with more than around. So, hello everyone, we are trying to be FLEPS, competing as a IEEE International Myosa in 2026. And we have spent the last couple of weeks building a solution to exactly the same problem. We continuously tracks 5 parameters at once: heart rate, oxygen saturation, stress levels, motion, and environmental conditions. And the moment something abnormal happens, the system responds instantly. Alerts are triggered directly on the wearable device, reflected live on the local dashboard, and synchronized to the cloud for remote monitoring and analysis. BioSync is designed to be more than just a health tracker. It's an early warning system built to detect problems before it becomes emergencies. Now let's take a closer look to what BioSync is, how it works, and how we implement it into it.
Picking up from my introduction, let's dive directly into BioSync's architecture. BioSync relies on a decentralized edge-first processing model. Instead of passing raw data to the cloud for analysis, the ESP32 performs all signal processing, anomaly detection, and alert logic locally on the wrist. This ensures zero latency, life-saving alerts, even if the Wi-Fi connection completely drops. A hardware stack is built around a dual-core ESP32 powered by a 7.4-volt lithium polymer battery. This prevents undervoltage brownout resets when the Wi-Fi radio draws 200 mA spikes. On a shared 400 kHz I2C bus, we run a MAX 30102 pulse oximeter, an MPU 6050 IMU, a BMP 180 barometer, and an APD S9960 gesture sensor, alongside a DHT11 sensor via a single-wire GPIO. To manage these sensors simultaneously without crashing, we engineered the firmware using free RTOS. Core 0 handles sensor polling, digital signal processing, and OLED rendering. Core 1 is entirely dedicated to Wi-Fi and MQTT telemetry. We utilize free RTOS, critical sections, and mutex locks to safely share a vital data struct between the two cores. This eliminates I2C blocking and ensures continuous smooth execution across the entire device. For cardiovascular tracking, the MAX 30102 collects red and IR light reflections at 100 Hz. First, we use an IR threshold of 50,000 counts for reliable arm detection. Then we utilize a peak detection algorithm for real-time heart rate, a rolling 100 sample buffer for continuous saturation of peripheral oxygen calculation, and we track RR intervals to compute heart rate variability, specifically RMSST. This gives us deep clinical insight directly on the wrist. Simultaneously, the MPU 6050 tracks user kinematics every 200 milliseconds. It classifies movement into low, medium, and high activity. Crucially, it calculates the 3D accelerometer magnitude vector. If the device detects a sudden impact spike above 2.5 Gs, it flags a fall event. Because fall detection is so critical, this immediately bypasses all other logic and forces the system into an emergency state. We also capture the user's environment. The DHT11 monitors ambient temperature and humidity, while the BMP 180 tracks barometric pressure. We included these because psychological stress is deeply impacted by harsh environmental conditions, like extreme heat in industrial, mining, or athletic settings. These contextual data makes the alerting system much smarter than a standard heart rate monitor. All of this raw data feeds into a custom edge-computed stress index, a 0 to 100 score. The algorithm normalizes and weighs 4 components: heart rate variability at 40%, heart rate elevation above a personal locked baseline at 30%, physical agitation at 20%, and heat stress at 10%. This provides a holistic, continuous view of the user's psychological load. This intelligence drives our adaptive alert state machine, which evaluates conditions every second. If saturation of peripheral oxygen drops below 94% or heart rate exceeds 110, the device enters a caution state, triggering a non-blocking haptic pulse pattern. If saturation of peripheral oxygen drops below 90%, heart rate exceeds 150 or a fall occurs, it escalates to critical. It instantly triggers localized physical feedback. A piezo buzzer on GPIO 25 sounds continuously. A coin vibrator on GPIO 26 activates and the OLED flashes an SOS. This failsafe operates entirely independent of the cloud. While the device handles the physical emergencies locally, Core 1 packages a highly optimized 300-byte JSON payload and publishes it over an MQTT broker every 2 seconds. We developed a React dashboard that subscribes via WebSockets on port 8084 for live fleet monitoring, allowing caretakers to track priority vitals with sub-3-second latency. We also connected the MQTT stream to Grafana dashboard for persistent time series historical tracking, perfect for remote doctors. In validation, BioSync performed flawlessly. We achieved on-rest alert latencies of less than 1 second and remote telemetry updates every 2 seconds without a single I2C bus hang. By combining open source hardware, free RTOS edge computing, and comprehensive web dashboards, BioSync proves that affordable devices can deliver enterprise grade, life saving observability. Thank you to the judges for your time.